In this video, this is the fourth of our series of videos on using certain algebraic techniques to help us find limits. This video is going to be focused on finding limits as x approaches infinity or minus infinity, particularly in rational functions. And so the basic technique that we're going to apply here is to multiply the numerator and denominator by 1 over x to some power, some constant power. And we're going to examine the end behavior this way. Now, in rational functions, usually what happens is when you try to take limits as x goes to infinity, you get the indeterminate form infinity over infinity because the polynomials in the numerator and denominator, unless they're constants, are always going to go toward infinity or minus infinity as we let x go to infinity, or as x goes to minus infinity, we get the similar result. So these are going to be indeterminate forms, and this little technique shows you something that we can do here. So what we can do is we can take the highest power in the denominator, the degree of the denominator, and take that power and multiply by the reciprocal of that power function. So here the highest term in the bottom in terms of power is x squared, so we're going to multiply by 1 over x squared. We're going to do that in the numerator and the denominator. Okay, and so certainly if x goes towards infinity, x is not 0. We're way out past 0, so we can not worry about the fact that this might be undefined there. So here we put this in the numerator and denominator, so that's legal to do. And then what we do is we distribute. So we get 2x squared over x squared minus 50 over x squared. In the numerator and denominator, we get 6x squared over x squared plus 7x over x squared plus 10 over x squared. Now we simplify where possible. X squared over x squared is 1, so this is just 2 minus 50 over x squared for the numerator. The x squareds cancel here, so that's 6. One of the x cancels here, so this is 7 over x, and then we have 10 over x squared. Now we can use you can use the laws of limits. It said the limit of the quotient is the quotient of limits. So we can take the limit of the numerator and denominator, and then we can also use the sum rule for limits. Says that we can take the limit of each piece. So basically we're taking a limit of each little piece here. So this is limit of 2 minus limit as x goes to infinity of 50 over x squared over the limit as x goes to infinity of 6 plus the limit of 7 over x plus the limit is 10 over x squared, all as x goes to infinity. Now what happens to these here, we need to know the fact that if you have a constant on the numerator and the denominator is going toward infinity, then the whole fraction is going toward 0. So these three limits here all go to 0. But these are constant functions, so of course 2 stays 2 no matter what you do. So as x goes to infinity, that doesn't affect this 2, so that limit is 2. This limit here is 6. And so these terms right here go away, and we get 2 over 6, which is 1/3 for the limit. So this says that the graph is approaching the horizontal line, y equals 1/3 on the far right. So one thing I want you to notice here is that ultimately these terms here, the 50, the 7x, the 10, those terms essentially didn't really have any effect on it because once we finally did this technique and applied the limit, those terms actually all went to 0. The only ones that really mattered were the 2x squared over 6x squared. So it turns out that the limit as x goes to infinity of 2x squared minus 50 over 6x squared plus 7x plus 10 is the same as the limit of just the leading term in the numerator divided by the leading term in the denominator. In other words, it's the same as the limit of 2x squared over 6x squared, which reduces to 2, 6. The limit of 2, 6 is 2, 6, which is 1/3. And so there's our limit. And we should be able to verify this graphically by seeing that y equals 1/3 is going to be what the graph approaches that. Here it approaches that asymptotically. So we see here on the far right, I've graphed in this red line y equals 1/3, and we see that the graph on the far right is coming up closer and closer and closer to that value. This particular one is actually a continuous function. Notice that 6x squared plus 7x plus 10 is never 0. Okay, and so we get we're never dividing by 0. So this is actually one continuous piece. But we see on the far right that x approaches infinity, y approaches 1/3. It actually turns out if you let x approach negative infinity here, instead, all the steps would be the same, and these limits would still be 0, and these limits would still be 2 and 6. So in fact, whether you approach infinity or minus infinity, whether you're going to the far right or the far left, the limit is 1/3, and so it approaches that y equals 1/3 asymptotically. So in fact, this one has some sort of global minimum here, and the range is from whatever that minimum y value is, closed interval there, up to open interval at 1/3. This particular one never crosses that horizontal asymptote anywhere on the graph. Now we know on the far right, it's not going to cross the asymptote. It's going to be coming up from below. And the far left also, in some cases, the function could cross the asymptote in the middle, but in this case, it does not. Now, that was an example where we had the power was the same in the top and bottom for the highest power, so the degree was the same of the numerator and the degree of the denominator. Those were the same. And what we ended up getting for the limit then is going to infinity or minus infinity was just the ratio of these leading coefficients. Let's look at the next case. The next case is what happens if we have the degree is larger in the denominator. Well, again, you want to multiply by 1 over x to the power, where the power is the largest power in the denominator. So we want to multiply the numerator and denominator by 1 over x cubed. Distribute and cancel. So distributing here, you can see that, what we got. And then we do our canceling. All the things in the numerator still have an x in the little denominators. This one just becomes 7, and these have the x's in the denominator when we distribute and cancel. Now this time I'm taking limit as x goes to negative infinity. It actually doesn't matter on a rational function whether you go to infinity or minus infinity. The limit will be the same if it actually has a limit. So we apply our limit laws now. Our limit laws say the limit of the quotients, the quotient of limits, provided these limits exist. Here are the limit of the sums, the sum of the limits, and same in the denominator, provided all these limits exist and we're not dividing by 0. Now here, all of 5 of these limits right here are 0. The only one that's not a limit of 0 is this one right here. The limit is x goes in negative infinity of 7, which is 7. Of course, that makes the numerator 0, the denominator 7. 0 over 7 is 0. So notice, once again, all of these terms here really had no real effect. It's really just this bottom one that made the effect, or the first one, the leading term in the numerator and denominator, you might say. So we note that the limit as x goes to minus infinity of 4x squared minus 25 over 7x cubed plus 3x squared plus 8x plus 15 is the same as the limit as x goes to minus infinity of 4x squared over 7x cubed, which is just 4 over 7x, or 4/7 times x to the negative 1. So notice if we take the leading term in the numerator and denominator and just use those two, that reduces to a power function. Notice this is a power function with a negative exponent, or in other words, an x in the denominator, and we see that as we let x get bigger and bigger, that goes to 0. In fact, not only does this thing go to 0, we can say it behaves very similarly to 4 over 7x on the far right and left. We get some other little funky shape happening right here with some changes in concavity. It goes concave down to up to down here. So there's a flexion point somewhere in here and here. But eventually it looks a lot like 4 over 7x. Of course, we know 4 over 7x should be in the first quadrant decreasing concave down. So eventually this will be decreasing concave down. Somewhere actually in here it crosses the x-axis. It's still increasing concave down, and eventually it maxes out in here somewhere. Looks like maybe around this area. Has a maximum. Then it's concave down, decreasing, and somewhere it has an inflection point, maybe around this vicinity, somewhere in here, and it goes concave up, decreasing. So there's some interesting stuff happening here. It's maybe a little bit hard to see on this particular picture, but we have some inflection points and things. But we know from some point out it behaves a lot like 4 over 7x. So once you get past this last inflection point, wherever it is, maybe somewhere in here, it's all decreasing concave up, approaching the x-axis, just like 4/7 x to the negative 1. And similarly over here, this one eventually it looks like 4/7 x to the negative 1, or 4/7x. That's in the third quadrant, and that's decreasing concave down like this. And so we know that in this quadrant right here, we get that. Maybe we could, this might be an interesting one to actually take a look at in Graphmatica. Let me pull that up and see if we can type this in. Parentheses around the numerator, 4x squared minus 25 divided by 7x cubed plus 3x squared plus 8x plus 15. Okay, there's our graph. And let's look at some. Let me also graph just the ratio of those first terms, which was 4/7x. Okay, so the green graph and the red graph should look like each other eventually on the far left and far right. Not at all like each other in the middle, perhaps. So let's look at the far right here, far left first, which is what we were actually doing there, I think, taking the limit as we go to minus infinity. And notice that this is coming from below. So if I zoom in there close, let's see. Let's do some grid range here. Let's go from negative 20 to negative 2. But let's zoom in a little closer on the y's. Negative 0.1 to 0.1. Let's see what that looks like. There you can kind of see some interesting things happening. Okay, if we zoom in on that scale there, you'll see that somewhere here the original function is, see this part here is concave up, right here. There's a minimum here. And actually this thing is, if you go from the left, it's coming down, concave, left to right is coming, decreasing, concave down. Somewhere about here or so, somewhere right in here, there's an inflection point, and it switches to, maybe it's about here or so, concave up, still decreasing. Then it hits a minimum, then it turns around and is increasing, concave up. But the thing I really want you to see about this is notice that once you get past this inflection point here to the left, it looks a whole lot like just that power function. In fact, the further you go out, it's hard to even tell the two apart. Okay? And of course, the reason for that is that all of these terms, all of this part, when you write in this form, all of this stuff right here is going to 0. I'm doing it pretty quickly. Okay? Let's also take this and look at some other parts of the graph. Okay, let's look right in here. Notice it does have a vertical asymptote there. If we were examining this a little more closely, let's see, where would that happen? Somewhere there's a place, there's one x value that makes the denominator 0. Look at, with the degree 3, there's potentially 3 places, but it looks like from our graph there's only one. But there's exactly one place, one x value, and whatever that x value is, here it is. Looks like it might be -1. Okay, it's either -1 or something close to -1. Let's see. Let's look at a point table. No, it's not -1. It's something else. Okay, it's something between -1 and -2. See, notice that the original function, when I plug in -1, I get -7. So -1 is actually down here at negative. So there's a point right here at -1, -7. But when I plug in -2, it's positive right here. So somewhere in between there, we got an undefined place. So anyway, it's -1 point something is our vertical asymptote. Okay, let's look at, let's see if I can just graph, let's say maybe this portion of the graph. Now that's kind of an interesting part of the graph. In this part of the graph, it doesn't look at all like the green power function, but it looks like we have a function that's increasing concave down right in this part. And somewhere about in here, maybe around 0, maybe not exactly there, but somewhere around in here, there's an inflection point where it switches to concave up, increasing for a little while, and then another little inflection point where it switches to concave down, increasing. So it looks like it's increasing all this way. Now, let's look what happens when we go over this way. Let's zoom in on this part here, say from 2 to the right. So let's change our grid range to go from, say, 2 to, let's go out maybe 20. But let's zoom in pretty close. Let's go in, again, -0.1 to 0.1. Let's just see what happens if we look just that close. Okay, now we can see some things that are happening as we zoom in more closely here. Somewhere here it crosses the x-axis. Looks like maybe that might be at 2. Let's see here. Now, no, it's not 2. It's we could work that out. It's when the numerator is equal to 0. Okay, that factors as 2x plus 5, 2x minus 5. It's 2.5. So, yeah, 2.5. That makes sense. 2 is over here. There's 2.5, 3. So it's actually 2.5, and it actually crosses over here at -2.5 also. That's where that graph crosses right there on the x-axis. All right, now let's look what happens. So this part right in here is increasing concave down. Somewhere in here, about here, it reaches a local maximum and turns around and starts to decrease concave down. And then somewhere, maybe around in here somewhere, it hits an inflection point, and from there on out, it's concave up, decreasing. After you pass that inflection point, it starts to look a whole lot like that power function. In fact, as we go further and further to the right, especially this part right in here, it starts to get extremely close to that. In fact, it's hard to really tell them apart on this scale. But notice that both of them, as you go further and further right, are getting closer and closer to the x-axis. So, the limit on both sides, the main thing we were pointing out at the moment, was the limit as you go to -infinity or infinity is 0. In fact, this will always happen when the degree of the denominator is larger than the degree of the numerator. And not only that, you can tell how it's going to approach the x-axis by looking at that ratio of leading terms in the numerator and denominator. That power function, if we understand its behavior, then the behavior at the ends, as you go to infinity and -infinity, that's going to be the same behavior for the rational function. Okay, now what happens? So there's sort of 3 cases. The case 1 was when the powers were the same in the top and bottom. The degree was the same in the numerator and denominator. And when the biggest power was bigger in the bottom, so the degree of the denominator is larger than the degree of the numerator, then we had a y-axis, x-axis, y equals 0 is the horizontal asymptote. The x-axis is the asymptote, y equals 0. If the degrees are the same, then you get y equals some whatever these ratio of coefficients here. That's our horizontal asymptote. But it turns out if the power is bigger in the numerator, we don't get an asymptote. So this is a case where the limit does not exist. Now, technically speaking, we can't really apply some of the limit laws below because some of these limits don't exist. But in practice, really, the basic technique still kind of works out. We take the largest power in the denominator and multiply by its reciprocal. We use that same technique and distribute and cancel. We see that when we take these limits, This one goes to a constant. These all 5 go to 0. But this limit goes to infinity. Okay. And let's see, that's just a square in it. It's the same limit with the square or not, but so this turns out to be infinity. Now technically we're kind of breaking a few rules here, because this limit, to say this limit is the limit of the quotient and then the sum of the limits, assumes that all these limits exist. And of course this limit is x goes to infinity of 4x squared does not exist, so the limit of the numerator does not exist. So technically our rules don't apply, but it actually still kind of works out here. So what happens here is x goes to infinity of this. Again, we can ignore everything but the leading term here and here. So we get 4x to the 5th over 3x squared, which reduces to 4/3 x squared. Well, we know that 4/3 x squared goes to infinity on the right, and of course if you take the limit as x goes to minus infinity, 4/3 x squared also goes to infinity. Now so this is going to have end behavior like 4/3 x squared. Also notice if we do long division, this is might be a little bit complicated long division problem here, but you could do it by hand. I did it with a calculator that would do a CAS calculator. But you can do this and get a long division, and notice that you get a polynomial plus a fractional remainder. As x goes to infinity, this fractional remainder goes to 0. So what happens is that as x goes to infinity, this thing gets closer and closer, kind of like an asymptote. Usually we reserve that word for lines, but it sort of asymptotically approaches this parabola. So it approaches the graph of this parabola, y equals 4/3 x squared minus 28/9 x plus 172 over 27. It actually gets closer and closer to that. But of course we know this parabola on the ends behaves more or less like the parabola 4/3 x squared. Okay. So here's a graph where all 3 of these are graphed together. In blue we see the actual original function, and notice in the middle it doesn't look at all like these 2 parabolas. You know, it's got a vertical asymptote right here. Let's see what that is, that vertical asymptote. Well, it's whatever makes that denominator 0. Don't know. Looks like it's close to 2, -2, but don't know for sure. I'd have to investigate further. But it looks like we got some interesting stuff happening here. It looks like we've got increasing concave down. Somewhere there's an inflection point, increasing concave up. Another inflection point, increasing concave down, a local maximum in here. Then it comes back down, decreasing concave down. There's an inflection point, and then it switches to decreasing concave up. Somewhere there's a minimum. And from there on, it looks like it's increasing concave up. Once you get past that last minimum, it's starting to look more like a parabola. To the left of this inflection, of this vertical asymptote, looks like it's all concave up. Decreasing concave up reaches a minimum, increasing concave up approaching this asymptote here. Now, once you're to the left of this minimum, it looks a lot like the parabola. Now, the actual purple one here is this function 4/3 x squared minus 28/9 x plus 172 over 27 is that, and you notice that it actually becomes almost indistinguishable from the purple graph as you go further and further out here. Of course, they're not exactly the same, just like a horizontal asymptote is not exactly the same as the function when it has one of those, but it does approach this sort of quadratic thing. Now, as far as the basic shape of it, though, notice both the original parabola, original function, the parabola that approaches the quadratic function, and just the quadratic function just given by the first term of that. So the first term is the 4x squared, 4/3 x squared, which is the same as just the leading term over the leading term here, 4x to the 5th divided by 3x cubed, 4/3 x squared. That's the y equals, that's the green one, and they have the same basic shape. So you can see that little parabola shape going on the ends. Okay, so that shows you what we can do with that. We'll come back and look at the next video and look at squeeze theorem in action.